Branch, can you see the screen and hear me? Can you guys hear me?
Yeah, I can hear you.
Okay, and you can see the screen, right?
Yeah, yeah.
Okay.
Professor, could I ask a question, or are you
Yeah.
prepared?
Yeah, go ahead. Yeah. Go ahead, Branch.
Oh, hold on, I can't hear you. Just a second. Say again?
Maybe.
Oh, it's really faint. I've got my volume turned all the way up.
Oh, really? Let me see.
could try searching for sound input on settings.
That's what I'm looking for.
There should be a search at the very top.
So I looked at sound. So what should I search for?
Sound input.
I can hear him.
Hmm.
I'm at max volume over here. You can hear me well?
Oh, I'm sorry, my bad. I had my headset plugged in.
Oh, I had the thing at max.
Yeah, I'm sorry about that. Hey, anyway, my question was, if you have a minute, on the Schottky barrier diode, the vacuum level bends with the energy bands, and I'm having a hard time wrapping my head around that. I thought it should just be a constant.
Sorry, I'm just a second. I'm so I have two computers on. You guys can still see my screen, right? With the device and everything?
I can hear you, but I don't know. I can't see it anymore.
Really?
Oh, wait a second. Yeah, all I see is like the setup screen. It says join audio, share screen, invite others.
can't see this.
I can't. I don't know if other people can or not.
Can somebody unmute?
See it.
What?
I can't see.
Austin, on the chat, Austin says he can't see anything.
I can't see anything either.
Well, we can see something. It's just no. It's just like your setup screen. It says join audio, share a screen, or invite others. There we go.
What now?
Yes.
Okay.
Anyway, I don't know if it's too late to ask, but
Yeah, I'll answer later on.
okay,
Sorry.
great. Thank you.
All right. Sorry about the snafu. Today's lecture is the next 4 lectures are perhaps among the most important, and you will be tested on these in the final exam. So we'll be discussing in the next 4 lectures MOS structures, metal oxide semiconductor transistors. Or we'll first start off with metal oxide semiconductor capacitors, and then based on that, we'll move to the 3-terminal MOSFET structure. As I've told you a couple of times already, the MOSFET is perhaps the most important microelectronic device today, because 99% of all devices that you use are based on MOSFETs. I've given you a preview of 3-terminal devices in the last class and pointed out that they basically have the advantage of being an active device, meaning that you can get power gain, which means the change of power at the output terminal is more than the change of power at the input terminal. The energy doesn't come out of thin air, it's extracted from the battery, okay? So with that, let's look at an isometric view of a MOSFET at the top of the screen, where we see the source, the drain, and then in the middle you have the channel, and then you have the gate electrode, which straddles the channel, where the electrode is separated from the channel by what's called the gate oxide, which is an electrical insulator, okay? This is the overall topology of the device is very similar to what we discussed last time in the context of the JFET or the MESFET, okay? But it turns out the MOSFET has several advantages over those other 2 devices, primarily because the gate is electrically insulated from the channel, and therefore the input gate leakage current in principle can be lower than that in the case of the PN junction gate or the Schottky gate for the JFET or the MESFET, okay? So how does this device work? Well, like all devices, we analyze them in terms of the band diagram, which is shown in the middle in equilibrium. How can I tell it's an equilibrium? Well, I see that the Fermi level, EF, is flat throughout the structure, and that's a hallmark of a device in equilibrium, okay? I'm drawing the band diagram now as a function of horizontal position, starting from the source at the left, channel in the middle, and drain on the right-hand side. And as I've told you before, you always want to draw the band alignments with respect to the equilibrium Fermi level, initially far away from the junction. Now, in this case, we have 2 PN junctions connected back to back. You have the N plus source to the P channel, that's one junction, that's a PN junction, and that's kind of connected back to back with the N plus drain P channel on the right-hand side, right? Now, clearly, if I have 2 PN junctions connected back to back, I forget about the gate for a second, and I applied either a positive or a negative drain bias, you'll see that one of the PN junctions will obviously be forward biased, and the other one will be reverse biased. And since the 2 of them are in series, the reverse bias junction will control the current to the structure, and the only current that you can get through the device would be that for a reverse bias, sorry. Reverse biased PN junction. I got distracted for a second. For some reason with Zoom, although the default mode is everybody is admitted automatically, for some reason several people have to wait. I've never quite figured that out. So anyway, so regardless of the polarity of the voltage that you apply to the drain, one of the junctions will obviously be reverse biased, and the transistor will not conduct significant current other than the leakage current of the reverse bias junction. All right. Now, so let's look at the band diagram and see if we can make sense of it. Well, in the N plus source and the N plus drain, you can see that the conduction band's closer to the Fermi level, as it should be. While in the P-type channel region, you see that the valence band's closer to the Fermi level. And then you join the band edges smoothly, and you see this potential barrier in the middle of the channel, right? But if you look at it carefully, it's like a PN junction barrier. If you take a cut in the middle, say, it's like a PN junction band diagram connected back to back with the other PN junction back to band diagram that I was mentioning in a second ago, right? So under these conditions then, if I'm an electron sitting in the conduction band of the source, I can't go over to the drain because I see this potential barrier created by the channel. And that potential barrier is nothing but the built-in junction potential of these PN junctions, all right? Now, I turn my attention to the gate electrode, and let's see what happens if I apply a positive gate voltage. Well, remember the principle that like charges repel each other and unlike charges attract each other. So if I apply a positive voltage to the gate, I'll be dumping positive charges. So if I apply a positive voltage to the gate, I'll be dumping positive charges on this gate electrode, and those charges will repel the majority carriers in the channel, which are mobile holes. Therefore, it will push the holes away from the surface region over here, okay? Make the surface less p-type because of this electrostatic effect. Now, because the gate is electrically isolated by this gate oxide, hopefully there's no current flowing in that direction. Okay? It's just like two plates of a capacitor. The gate electrode is one of the capacitor plates, and the semiconductor channel is the other plate of the capacitor, okay? And the dielectric in between is the gate oxide, as well as we'll see in a second, in series with the gate oxide, we'll have an effective dielectric, which is the depletion region forming in the channel, which is a voltage dependent parameter, as in the case of the depletion region capacitance of a PN junction, all right? Okay, so let's see what the band diagram does when you apply this positive gate bias. As I said, you push away the majority carrier holes in the channel because like charges repel each other, and therefore this region becomes less p-type. How would that be reflected in the band diagram? Well, this part of the band diagram should move down in energy, right? Because the valence band has to now move farther away from the Fermi level. Well, if it moves down in energy, what happens to this potential barrier height? Obviously, it'll drop, right? If you drop that barrier sufficiently by applying what's known as the threshold voltage of the transistor, then these electrons can spill over from the source or the drain into the channel, and you create basically a sheet of electrons in the middle of the channel. What you have then is basically a gate voltage induced N-type resistor in the channel, which forms what is called an N-type inversion region, connecting the source and the drain, okay? If you think back to our lecture from last week, it's kind of like the JFET or the MESFET, but in the JFET and the MESFET, you preformed the channel by doping, right? And you then pinched off the channel gradually by applying a reverse bias to either the PN junction or the Schottky barrier, okay? On top of that, of course, once you start flowing significant drain current by increasing the drain bias, you saw that the channel got pinched off more and more closely near the drain end of the channel, okay? And ultimately the current saturated. Well, that part of the story is applicable over here also, as you can see in these IV characteristics. So depending on these gate biases, the more positive the gate bias, the more negative electrons you induce in this inversion channel. Therefore, the channel becomes more conductive. And you can see that by the slopes of these IVs in the so-called linear region. That's the linear region over here. The right-hand side of this dotted line is a saturation region. And these corresponding voltages are known as the VD sat along the dotted line over here. To the left of that, we have basically a resistor. You basically have a resistor. So higher the drain voltage, the current goes up. But the slope of those resistors becomes steeper, meaning that the resistor becomes more conductive as the gate voltage increases, which makes sense, right? The more the positive gate bias, more electrons in this inversion layer. Therefore, this induced N-type resistor will become more conductive. All right. But then, as current flows from the source to the drain, as in the case of the JFET and MESFET, the potential in the channel near the drain end keeps increasing to whatever the drain voltage VD is. What is the potential in the channel near the source end? Well, remember the source is always assumed to be at ground. Therefore, this is always at the ground potential, while the drain goes up to VD, and to the gate we apply a VG. Okay, so as the drain voltage keeps increasing, the channel potential near the drain end keeps increasing, and at some point, when the voltage difference between the gate and the channel potential in the drain end reaches what's called VD sat, the channel gets pinched off, this inversion channel gets pinched off, and then the current saturates. Now that's shown more clearly in the next slide over here, where I'm showing cross-sectional views of the structure under different gate and drain biases. All right, so on the top, I apply a gate bias to induce this N-type inversion layer, shown by that dotted blue region, and the drain bias is initially 0, say. Then I slowly increase the drain bias. Current flows from the source to the drain, and in the process, the channel potential from the source to the drain, which I call Vx, if that is my x-axis, would increase initially linearly from the grounded source to whatever the VD, that's channel length, sorry, whatever VD is near the drain end, okay? But then, as the drain voltage is increased more and more, you see that the voltage difference between the gate and the channel near the drain end, which is always going to be VG minus VD, is going to keep decreasing, right? On the other hand, the voltage difference near the source end will always be fixed at VG minus 0. So that doesn't change as a function of the drain bias. But the voltage difference between the gate and the channel near the drain end keeps going down as VD goes up. As VD goes up, this voltage difference goes down. And when it goes down to a value called the threshold voltage, which I'll discuss in a second in great detail, you don't have enough effective gate voltage to channel potential to induce this inversion region shown in this dotted blue region over here, and the channel gets pinched off. All right. So if I was to plot the channel potential as a function of channel length, as in the case of the JFET, it will no longer vary linearly, but it'll curve up like this. Why? Well, it'll curve up because the current at any cross section, of course, has to be the same in accordance to KCL. You can also see that the effective cross section of this resistor, this dotted blue region, is higher over here than over here, and it's even smaller over there. To drive the same current across each of these cross sections, you have to, of course, have a higher electric field here, say at this slope, compared to the middle, somewhere in the middle, say, versus the highest electric field or the steepest slope will be near the drain end of the channel. And therefore, this curve bends upwards, as you saw in the case of the JFET or the MESFET. All right. Now, once you exceed this point, so that voltage corresponds to what is called VD sat, exactly as in the case of the JFET. Now, once VD is greater than VD sat, the current, the point at which the current saturates, the pinch-off region extends more and more into the channel. You have a very high electric field where the carriers that are pulled out of this inversion region travel as fast as they possibly can at the saturation velocity. And that's shown over here where I'm looking at the drift velocity as a function of electric field. So initially we have the ohmic regime, mobility times electric field, but at high fields, we saw that it gives you saturation drift velocity Vsat. And corresponding to this, if I was to plot the ID as a function of Vd, initially I'm in this region, so it's like a resistor, ohmic resistor, but then starts bending over because the channel gets more and more constricted. And once I reach Vd sat, it hopefully saturates at some ID sat, okay? And that's a family of curves that I see over here.
If
All
the
right.
if the channel is pinched off, how does the current flow at all?
Very good question. So that's a very interesting question. Now, just because the channel gets pinched off doesn't mean that there cannot be any current flowing. And in fact, if you think back to that, think back to what we discussed for the PN junction, remember, in the PN junction, even in forward bias, the depletion region is still there, right? It gets collapsed a little bit, but the depletion region in the middle, right, near the junction is still present, right? So it's the same kind of thing. So just because I have a pinched off region, all that means is the equilibrium carrier concentration over there would be 0, but that does not, and the charges over there would be the exposed, in this case, negative acceptor ions, but that does not mean that carriers can be injected and flow across that, okay? So if you ask to plot the potential profile, basically what's happening is I've reduced the potential barrier over here. These electrons have spilled over into the channel. And in this region, with increasing drain bias, the energy level will go down, of course, right? And essentially what I'm doing is I'm injecting carriers into the conduction band, and in this depletion region, they can go down this energy hill, okay? Exactly as in the case of the current flow across the depletion region of a PN junction. That's a very important question, so I'm glad that you asked that. Any questions? So look at this band diagram as a function of gate bias. So with gate bias, this potential barrier goes down compared to equilibrium. So that's Vg equal to 0, and then Vg positive. So the barrier has gone down. But then as the Vd goes up, the energy level of the electrons in the drain will keep decreasing. Remember, the energies are minus Q times whatever the voltage is. And that's the energy in the source, which is 0. So that doesn't change. So these electrons are injected. That's my depletion region. It does not prevent these electrons from flowing down this energy hill across this depletion region.
Just for the purpose of visualization, where is the current all flowing near the surface, or does it go deep?
That's also a good question. It's mostly near the surface, and we'll talk about those, in greater detail later on. But essentially, in this lightly shaded region, that's what the depletion region is, and we'll see that we have equipotential contours like that. Okay, you have to figure out what the electric fields are. All right, and the electric fields will be perpendicular to the equipotential contours. And basically, you'll see that the current flows mostly at the surface, but near the pinch-off region, it will dip down a little bit and then go into the drain. But it's, for initially, let's assume that it's mostly near the surface, okay? Within the top 50 to 100 angstroms or so. These are all great questions. All right. Oh, there's a typo in this PowerPoint slides. These 2's are supposed to be minus. So fix those. I think I fixed them on Canvas. Okay, so that's when strong saturation is, when the gate voltage is higher than the so-called threshold voltage, which is required to form this inversion layer, and the drain voltage exceeds Vg minus Vt, okay? Why is that? Well, if the drain voltage is Vg minus Vt over here, so that's equal to, say, Vg minus Vt, and the gate voltage is held at, say, Vt. What is the voltage difference between this and the drain? It'll be Vg, sorry, it's Vg. So it'll be Vg minus Vt. In other words, once I reach Vd sat, so that's my Vd sat. Once I reach Vd sat, the voltage difference between the gate and the channel becomes Vg minus Vt equal to Vt, right? So I'm barely at the onset of forming this inversion layer. Okay, and that's where the channel gets pinched off. Okay, so that was sort of a preview of the MOSFET. What I'm going to do in the next 4 or 5 slides, in fact, in the next lecture, set aside the MOSFET for a bit and look at the one-dimensional MOS capacitor structure. Essentially, what I'll do is I'll look in the middle of the channel, take a cut as a function of depth, and look at this part of the structure and forget about the source and drain from now on, okay? Now that looks like a capacitor because the gate electrode is like one of the electrodes of a MOS capacitor. The oxide in the middle is like a dielectric, and the semiconductor over here is the other electrode, except that the other electrode really starts from the undepleted part of the channel. Okay, so the part that's heavily shaded is the other electrode, and this dielectric of the capacitor. So you have the capacitor over here, you have the 2 electrodes. Okay, now let's flip that over this way. So one of the electrodes is the gate electrode, the other one is the undepleted part of the semiconductor. And the dielectric is now made up of 2 parts. It's made up of the gate oxide in series with the depletion capacitance, which is this slightly shaded region over here. Now one finds that the depletion capacitance or the depletion region is a function of the gate voltage. As the gate voltage becomes more and more positive, I push more and more holes away from the surface, the depletion region expands, and so the depletion capacitance, which we saw in the case of the p-n junction depletion region, was given by the dielectric constant divided by the depletion width, that will keep decreasing as the depletion width keeps increasing. So you end up getting a voltage dependent capacitance in the MOS cap structure. So for the next lecture, today's lecture and the next lecture, let's ignore the source drain and just look at this one-dimensional structure, this MOS capacitor, okay? And what I'm doing in the next slide is plotting the band diagram as a function of depth in this MOS capacitor structure, okay? Where to understand these band diagrams, I now look at the MOS cap structure by turning it by 90 degrees. So that's my gate, that's my metal gate, okay? Oxide, and then the semiconductor. Okay, and that's the band diagram, and I'm showing the band diagrams for that MOS cap structure, but I've turned the structure by 90 degrees. All right, and I'm showing the band diagram for different gate voltages. Initially at the top for a gate voltage of 0, and then with different gate voltages, negative and positive. Okay, so that's a voltage on this electrode. Now, let me make a confession. For these band diagrams, initially, I'll be cheating a little bit, and I'll be assuming a so-called ideal MOS structure. What do I mean by that? I am assuming an ideal structure in the sense that if my applied voltage to the gate is 0, we know, of course, that the Fermi level has to be constant everywhere, okay? So I see the Fermi level in the gate, which I call EFM, because it's called EF in the metal because for all practical purposes, the gate is like a metal electrode. It may not be an actual metal. In many cases, what masquerades as a metal is a highly doped polycrystalline layer, but functionally it's like a metal, okay? So it's interesting. MOSFETs were first made with the actual metal aluminum. Then for many years, people used a highly doped polysilicon gate to act as a metal. But now things have kind of come back full circle. People have moved back to actual metal gates, not aluminum, but other gates to optimize the device that I'll discuss later on, okay? Now, in this case, where the structure is in equilibrium, where the voltage applied to the gate is 0, I see that the Fermi level in the metal gate lines up with the Fermi level in the semiconductor EFS, okay? And I've somehow chosen the parameters where under these conditions, the bands in the semiconductor are flat, okay? EC and EV don't change as a function of position. That is known, therefore, as a flat band condition, okay? And that's a very important condition because what do I get if I have flat bands? What is my electric field in this direction in my semiconductor? Can anyone answer that? In the semiconductor, what is my electric field under these conditions?
0.
Very good. Because electric field is given by minus dV dx. The voltage is connected to the band edges as EC, for example, is minus Q times voltage. Therefore, electric field would be plus 1 over Q dEC dx, right? So if my band edges are flat, the electric field has to be 0, okay? Now, what will happen is in an actual structure, that's not necessarily true. If I apply a 0 voltage, we'll see there'll be some band bending in the semiconductor. But I've chosen parameters in the semiconductor and the gate electrode where there is no band bending under applied voltages of 0. Another way of saying the same thing is my flat band voltage is assumed to be 0 in this idealized structure. In the next class, we'll fix that assumption, all right? Now, the flat band voltage is a nice point, reference point, because then you can measure the band bending in the structure, semiconductor or the oxide or everywhere else, with respect to this flat band conditions. Okay, and that's in fact shown in the next few slides. So initially, let's look at what happens if I apply a negative voltage to the gate. All right. Now, mind you, in this direction, you should not have any current flow, right? Because you have an insulator, oxide. Okay, so these are the two plates of the capacitor, as I've told you. That's one plate, that's my gate. The other plate of the capacitor is the undepleted part of the semiconductor. While the dielectric is a funny kind of a dielectric. It's made up of this fixed gate oxide, but then in series with that, we have the depletion region, C depletion, with the depletion width W, which is a voltage dependent depletion region. Okay, so you have a fixed oxide thickness Tox in series with the voltage dependent depletion region in the semiconductor. And the two of them together constitute the dielectric of this MOS capacitor structure. If I apply a negative gate voltage, what's going to happen to the majority carriers in the semiconductor? Well, the majority carriers in this case are assumed to be holes. And I know that because my Fermi level is closer to the valence band. The mid-gap level is in the middle. And then if I apply a negative voltage, once again, unlike charges attract each other. So I'll be attracting these mobile majority carrier holes to the surface, and I'll get holes induced in the valence band. So this is a scenario where the semiconductor was p-type to begin with because of doping, but now electrostatically, because I've applied a negative voltage, I'm pulling more holes towards the surface, and that's reflected by the valence band moving even closer to the Fermi level than it was in the bulk. This scenario is known as accumulation because I'm accumulating the majority carriers, in this case, the holes, electrostatically by applying a gate voltage. All right. Now, it turns out that's not that interesting because what gives rise to the current flow is when I have a so-called inversion region. Why is it called inversion? Well, this is a p-type material to begin with, but I'm inducing electrons in this channel. So I'm inverting electrostatically the carrier type in the channel. And that's shown in the next two band diagrams, C and D. Okay. Now, to form an inversion layer, I have to apply a positive gate voltage, as I mentioned. Okay. Now, the positive gate voltage initially will push away the holes from the surface region, and that's reflected by this valence band edge moving farther away from the Fermi level. So now the surface is more p-type. Okay. Sorry, it's less p-type. Okay. I'm pushing away the holes away from the surface. But if I push away the holes, I'll end up exposing charges in the depletion region, which are these negatively charged acceptor ions, right? Remember, it's acceptor ions which create the holes in the valence band. Well, as I push away the mobile holes, the acceptor ions, which are ions locked in the lattice, those are not mobile, they're exposed, right? And these are what form the depletion region in the semiconductor of a certain width W, all right? And I keep going. As I increase the gate voltage, the bands will bend more and more. And at some point, the EI, the mid-gap level, will touch the Fermi level in the semiconductor at the surface, right? Now, who can tell me what the carrier concentration right at this interface is at that point? When EI bends and meets with the Fermi level at the surface, right in this interface region, can anyone tell me what the carrier concentration of electrons or holes is? Well, remember in chapter 4, we saw that electron concentration, for example, was given by the intrinsic carrier concentration, e to the power EF minus EI over KT. And for holes, it was flipped. It's Ni e to the power minus EF minus EI over KT, right? So if my intrinsic level meets up with the Fermi level, EF minus EI equals 0, therefore the carrier concentration of either electrons or holes becomes Ni. So at that point, I've electrostatically converted the semiconductor into an undoped intrinsic semiconductor. It really isn't undoped, it's doped p-type to begin with, but electrically it behaves like it's undoped, and I have intrinsic semiconductor right at the surface. Now I like doing this experiment so much, I keep going, I keep increasing the gate voltage, the bands keep bending. Now let's see what happens right near the surface, okay? So the intrinsic level has crossed the Fermi level, and from that point to the interface, the intrinsic level is actually below the Fermi level. Now, who can tell me what the semiconductor looks like between the interface and that crossing point? On the right-hand side of that, the intrinsic level is higher than the Fermi level, which is symptomatic of a p-type semiconductor, right? But between the interface and that crossing point, is the Fermi level in the lower half or the upper half of the band gap? It's in the upper half of the band gap, meaning that that region is starting to look like an N-type semiconductor. And that is known as forming an inversion region. Okay, I'm electrically inverting the carrier type of the semiconductor. I think someone had a question.
I just said N-type.
Okay, yes, that's the right answer. Okay, I keep going. The bands bend more and more and more. And at some point, what will happen is the Fermi level, the intrinsic Fermi level, which was initially higher than the Fermi level, will bend as far below the Fermi level at the surface as it was above the Fermi level in the bulk. Okay. Now, the difference between the intrinsic Fermi level and the Fermi level is defined by this parameter called Q phi f, which is known as your Fermi potential. I think we mentioned this in chapter 4. So Q phi f is this quantity, EF minus EI. Q phi f is EF minus EI, okay? Therefore, this Fermi potential, either in voltage units or energy units, is a measure of how strongly N-type or P-type the material is, right? So in the bulk, since EI is above EF, that tells you how strongly the material was doped P-type. But then once I reach strong inversion over here, if I reach the point where the intrinsic level goes as far below the Fermi level as it was above the Fermi level in the bulk, who can tell me what this inverted electron concentration at the surface is compared to the majority carrier hole concentration in the bulk? So initially, EI was higher than EF, right? So let's rewrite in this way. E to the power, if I absorb the minus sign, it becomes EI minus EF over KT. So initially in the bulk, the intrinsic level was higher than the Fermi level, and that's what I call my Fermi potential, right? And my question is, now at the surface, when I have strong inversion, I'm saying that the intrinsic level is going to be as far below the Fermi level at the interface as it was. Let me rephrase that. So once I reach strong inversion, I'm saying that the intrinsic Fermi level will be as far below the Fermi level as it was above the Fermi level in the bulk. So under these conditions, what would be my electron concentration compared to the hole concentration because of doping in the bulk?
The same.
Same. Very good. And that is known as the onset of strong inversion. And the gate voltage that you need to do that is defined as your threshold voltage. Okay. So when I have that, that's called strong inversion. While before that, you get what's called weak inversion. Okay. Now we'll see in the next couple of slides that once you reach strong inversion, the depletion region doesn't keep expanding any further, and the bands don't bend anymore. It gets more or less fixed. What is the band bending under those conditions? That strong inversion. Well, for the intrinsic level to cross the Fermi level, you have to have a band bending of Q phi f, and then to go below the Fermi level, another Q phi f. So the total band bending would be 2 times Q phi f at strong inversion, where the gate voltage is equal to the threshold voltage. Okay. That is what I'm showing in the next slide under inversion conditions. So here, I'm looking at the band diagram just in the semiconductor. Okay. I'm just focusing on this part of the band diagram. Okay. Oh, that reminds me, I forgot to mention a few other things. So in this band diagram, you see that the metal, of course, doesn't have a band gap. If I only worry about the Fermi level, the semiconductor does have a band gap. The oxide also has a large band gap. In fact, it's so large, the band gap is so large that I'm only showing conduction band over here. The valence band would be somewhere down below that I'm not showing for the sake of clarity. Now, what one defines are these quantities called the electron affinity and work function that we mentioned last time. What is the electron affinity? The electron affinity is the energy level between the conduction band and the vacuum level. The work function is from the Fermi level to the vacuum level. But what is done in the context of MOS structures is, instead of looking at the vacuum level as your reference point, the convention is to choose the top of the conduction band, the conduction bandage in the insulator, shown over here, as your effective vacuum level. I mean, you're free to choose any convenient reference potential energy, and so one chooses that rather than the true vacuum level. So I now define my work functions of the semiconductor and the metal with respect to the conduction bandage in the insulator. Okay. Now in these diagrams, as I've told you, you can figure out what the electric fields are by relating them to the band bendings. Okay. So for example, I can see the electric field points one way this way, the opposite way this way. More the slope, the higher is the electric field. You can in fact relate the electric field in the semiconductor to the electric field in the oxide. That's the slope in the oxide. Okay. In this first diagram, the electric field in the oxide and the semiconductor was 0. But in these diagrams, you see you have electric fields in the oxide and the semiconductor. The two electric fields are actually connected to each other. If you remember your EMAG classes, remember we see that across an interface of two dielectrics, what has to be continuous is called the electric displacement. Electric displacement is defined as the product of the dielectric constant, say of the oxide, and electric field of the oxide, equal to the dielectric constant of the semiconductor and electric field of the semiconductor. These are given by the band edges. These are the dielectric constant. Now, just for calibration, the relative dielectric constant of SiO2 is around 4, and that of silicon is around 12, approximately. So therefore, these slopes will have a ratio of 1 to 3. Okay. So these are known as electric displacements. Okay. Now, if you have a sheet charge right at the interface, actually, that has to be added to that. So if I have an interface charge, Q interface, that enters into this equation over here. All right, so what I'm doing is I'm looking at now this part of the band diagram and blowing it up, because I'm interested in figuring out what the inversion charge density would be once I reach threshold voltage or higher than that. Okay. So in this band diagram, the metal Fermi level is far to the left. It's not shown on the screen. Then I have the oxide, very large band gap. Okay. Of course, the bands will be bending. And then I'm just focusing on the semiconductor part of the band diagram, which is this part over here. All right. And I'm looking at inversion, because now I see that the intrinsic Fermi level EI has crossed the Fermi level. So that's the location where the carrier concentration of electrons and holes are both equal to Ni. On the right-hand side of that, I have more holes than electrons because the intrinsic level is higher than the Fermi level. But to the left-hand side of that point, the Fermi level is in the upper half of the band gap. So that now is looking N-type. This side is P-type, okay? The Fermi potential, like I said, is a measure of how strongly P-type or N-type the material is. In this region, it's the P-type because of the doping, acceptor doping. On this side, however, it's starting to become N-type because of the electrostatic effect of the gate, okay? The one parameter that you define in this diagram is called the surface potential, phi s, which is the maximum band bending that you have right at the surface. So phi s is from this region in the bulk to what you have at the surface. Okay, so that's a total voltage drop in the semiconductor. Now, based on what I told you on the previous slide, what is going to be the maximum value of phi s? Well, if I have a band bending of phi f, I reach this point, and then another phi f at strong inversion. So when phi s equals 2 phi f, I have strong inversion. And the claim is, beyond that point, the bands don't bend any further. It gets pinned at that point, okay? There's no more band bending, and that will give rise to what's called the maximum depletion width, as we'll see in a second, okay? Now, on the right-hand figure, what I'm showing is the integrated charge, integrated charge distribution as a function of depth. I call this x, okay? I call this x. From the interface, I call this point 0, all the way up to the bulk, which you can take the limit going to infinity, okay? Now, truth is, once the bands stop bending, which is this point, this integral will basically give you 0, right? Beyond that point, because you have space charge neutrality. So the only contribution to this integral will be when I have band bending going on, okay? Now, this integral, I'm calling QS, and has units of coulombs of charge per unit area. What do I mean by that? Well, if you look at this structure, I'm looking at this inversion region by integrating the charge as a function of depth. Here, x points downward, okay? And the charge density initially has units of coulombs per centimeter cubed, but then if I integrate with respect to x, dx, you'll get a charge per unit area, which is coulombs per centimeter square, okay? And the convention is to figure that out on a per unit area basis. In other words, you assume the area of this capacitor A is 1 centimeter square, and everything is figured out on the basis of unit area capacitors. Now, of course, real capacitors will not have any unit area, but that's no problem at all. So if I wanted the total charge, you simply multiply that by this QS, okay? But for most cases, we'll not worry about the A. We'll assume that to be 1, and we'll stick in the A at the very end as needed, okay? So these are all integrated charges, integrated as a function of depth per unit area, okay? And what I'm plotting in this figure is a semi-log plot of this charge as a function of the surface potential, which is the maximum band bending at the surface, okay? Let's see if we can understand that. Well, let's start off with this point of band bending of 0. If I have a band bending of 0, the bands are doing this. And what did I call that point? That's my flat band condition, right? So that corresponds to this diagram over here, right? Now, when I have flat band conditions, what is my net charge in the semiconductor? Well, if I have flat band, I have space charge neutrality, and the charges will be Q, all the positive charges minus all the negative charges, okay? What are the positive charges? Well, I have mobile holes. Any other positive charges? I don't have any donors. I mean, I could in practice, but in this case, suppose there's no donor type doping at all. That's all the positive charge that I have. What are the negative charges? Well, minus acceptor ions. It's acceptors which create the holes, okay? Minus any minority carrier electrons, in this p-type semiconductor, Ni square over p, right? That's generally going to be pretty small to begin with, okay? Now, when I have space charge neutrality under flat band conditions, P is equal to Na, and therefore the net charge is equal to 0. But of course, once I have depletion or inversion, I no longer have space charge neutrality, okay? So under flat band conditions, when the bands don't bend, the integrated charge or the charge per unit area is equal to 0, and therefore the integrated charge is also equal to 0, all right? When I apply a negative surface potential, the convention is the bands are assumed to bend upwards like this. That corresponds to this diagram. Under these conditions, you get an accumulation of the majority carriers. So now this whole concentration keeps going up. In fact, it will go up exponentially because all these carrier concentrations depend exponentially on the band bending, which is reflected by EI, okay? The Fermi level doesn't bend. And I forgot to mention one other thing. The true equilibrium is this scenario where the applied voltages are 0. Under these conditions, in this ideal MOS structure, the Fermi levels are constant. But then when I apply a voltage, the Fermi level in the metal and the Fermi level in the semiconductor split by whatever the applied voltage is, right? So therefore, these are not equilibrium conditions because the applied voltage is different from 0. However, because this is a MOS capacitor structure and there can be no current flowing in an ideal insulator, although I'm splitting the Fermi levels, the current flow in this direction is equal to 0. And as a result, in this particular structure, you have essentially what you could call a quasi-equilibrium. Quasi-equilibrium. Okay, so it's not a true equilibrium, but it's called a quasi-equilibrium because although I've applied a voltage, there's no current flowing in it, okay? And because I have a quasi-equilibrium, the Fermi level in the semiconductor is flat, and it's also flat in the metal, but the two are separated by whatever the applied voltage is, okay? So strictly speaking, I should call them quasi-Fermi levels, but because there's no current flowing, you can, it's like the separate Fermi level in the semiconductor and the separate Fermi level in the metal, because you have quasi-equilibrium. All right, so on the left-hand side, as the bands bend upwards, the sign convention that I've chosen is the phi s, the surface potential is negative, I get an accumulation of holes, okay? Under those conditions, we'll prove in the next slide, the whole charge, accumulated whole charge will vary as e to the power q phi s over 2 kt. Why do you get that exponential dependency? Well, the exponential dependency comes from this relationship over here, because this EI is a measure of the band bending, and EI at the surface will give you the surface potential. Now, you might say, just looking at this, it looks like it should be Ni e to the power phi s over kt. Why is it 2 kt? It's 2 kt because the band bending isn't the same everywhere, right? It's maximum at the surface of phi s, but then gradually goes down. Therefore, when you do the integration, you have to do this averaging over this whole band bending region. That ends up giving you a factor of 2. Okay? I'll prove it mathematically in the next slide, but this is the hand-waving argument. All right. Now let's go to the more interesting side, which is positive band bending, which is what's shown over here. So initially what happens is I only form a depletion region, right? Because the Fermi level, the intrinsic Fermi level hasn't crossed the Fermi level yet. I'm gradually forming this expanding depletion region. Now, what charges will I expose under those conditions? These will be these exposed, negatively charged acceptor ions that I've doped the semiconductor with, okay? The whole concentration goes down almost to 0 because I'm forming a depletion region. And initially, the minority carrier electron concentration is also negligible. So it's mostly the depletion charges that are exposed in the depletion region, all right? Now, how would the depletion width be related to the voltage drop across the structure? Well, we make use of that in a famous formula that I keep talking about, that we first derived in the case of the depletion region of a PN junction. And if you look back at your notes, you'll see that the voltage drop across the depletion region V is given by half Q doping, either Na or Nd, in this case Na, W squared over epsilon of the semiconductor. All right. Therefore, inverting this, you can see that W would be proportional to square root of voltage, then all these factors, right? So I bring all these factors to the left, and then I take the square root. So the depletion rate is going to be proportional to the square root of the voltage and some of these other factors over here, right? But what is the effective voltage drop? Well, that's my phi s, right? Now, mind you, I'm not saying that this is a PN junction, but the math is the same because I have to solve Poisson's equation or Gauss's law in this region, exactly as we did in the case of the depletion region of a PN junction. So we can simply steal that expression that we derived for PN junctions and apply that over here, okay? Now, what is the punchline? The punchline is we find that the depletion rate will scale as the square root of phi s as shown over here, okay? What will be the charge, depletion charge per unit area? That'll be given by Q Na times W. Na is the doping per unit volume. Na times W will give you the exposed acceptor ions, and then times Q will give you the charge. Therefore, in this depletion region over here, you have the ionized acceptors, and the depletion charge scales as the square root of the voltage or the square root of phi s. Okay. Now, as the gate voltage is made more and more positive, as I mentioned, the band bending will be more and more, the depletion region will keep expanding. But then when the band bending reaches 2 phi f, which is this over here, so when the band bending equals 2 phi f, that's the gate voltage corresponding to threshold voltage. Beyond that point, we assume that the surface potential doesn't change much at all. Well, in this figure, it's shown that the slope is becoming steeper. So depending on the structure, you can assume that it's almost like a vertical line, okay? The depletion region doesn't expand any further. The bands hardly change any further. It gets pinned at a band bending of 2 phi f, okay? And that's the onset of your strong inversion corresponding to a gate voltage of Vt. Now, what if I keep increasing the gate voltage and make it greater than Vt? Well, what's going to happen is the band bending, like I said, doesn't change any further. The exposed acceptor ion charge doesn't change any further. But all that will happen is I'll start dumping more and more inversion electrons in the channel. And that's what's shown over here. And it is those inversion electrons, which are shown in this dotted blue line, which connect up this N-type doped resistor, N-type source region to the N-type doped drain region. Everybody with me? As I told you, these are very important concepts, and you need to study this again and again because you will be tested on this. I can guarantee you that in the final exam, okay? Because MOSFETs and MOS capacitors are so widely used, all right? Under these conditions, once I reach strong inversion, one finds that the inversion charge density also scales exponentially with surface potential, e to the power q phi s over 2 kt, okay? In this case, in accumulation, it was minus, but here it's plus, okay? Once again, why is it exponential over 2 kt? Well, all that I need to do is look at this expression for, in this case, the minority K electron concentration, which scales as Ni e to the power phi s over kt. But then because it's not maximum band bending of phi s throughout, it decreases as you go into the semiconductor. Once you do that integral and the averaging, you end up getting a factor of 2 in the exponent. Okay. Now this curve is very, very useful because we'll be using this to explain the MOS CV behavior. A couple of slides down. And the way we'll do that is, as we discussed in the context of the capacitance of the depletion region, we said that if I have a fixed parallel plate capacitor, across which if I apply a voltage V, I'll induce a charge of, say, plus Q on one plate, minus Q on the other plate. And suppose the dielectric constant is epsilon, width is, say, W, and the area of the capacitor is A. We saw that in a fixed parallel plate capacitor, Q as a function of V will be a straight line, and capacitance would be Q over V. But in a semiconductor device such as this depletion region is voltage dependent. Therefore, Q over V will not be a straight line. It'll be some curve. If you have to define a voltage dependent capacitance as dQ dV. All right. What is dQ dV? These are nothing but the slopes of these curves at different operating points, right? And that gives you the voltage dependent semiconductor capacitance. That is going to be in series, in this case, with a fixed voltage independent oxide capacitance. Because remember, the structure is made up of an oxide of a certain thickness TOX. That'll give rise to an oxide capacitance, epsilon oxide over TOX, in series with the voltage dependent semiconductor capacitance. Let me call that CD as a function of V. Okay. And that CD as a function of V is obtained as dQ dV, which is nothing but the slopes of these curves. Everybody with me? I know it's kind of complicated the first time you see it, but the basic principles, not that hard. Now, I don't want to get startled or scared by the next slide. So the next slide, I actually derived this curve, and all that it involves is solving the Poisson equation, all right? The derivation is given in the textbook. You might want to go through that again on your own, but you'll not be expected to derive this expression in the exams. Anyway, it's going to be an open book exam, so even if I gave you this problem, you could simply copy. But it looks scary, but it's not difficult at all. Okay, so this is just solving the Poisson equation, where phi is my potential, okay? And this is nothing but dE dx, the divergence of the electric field, is equal to the charge distribution over epsilon. Now, the electric field is related to the potential as minus d phi dx. So electric field equals minus d phi dx or dV dx, right? So dE dx becomes the second derivative of the potential with respect to position, and that's given by the net total charge divided by the dielectric constant, okay? What are the possible charges? Well, the possible mobile positive charge are the mobile holes, and if you had any donors also doped in there, the immobile donors, minus the negative minority carrier electrons in this case, and acceptor ions, right? So this is the general expression where I assume that I have both p-type doping and n-type doping, all right? The next thing that you do is you write down the expressions for the holes and electrons in terms of the band bending. And basically what this is use these relationships over here, okay? And essentially what they tell you is the carrier concentrations change exponentially with the band bending, right? Because it's given by the intrinsic carrier concentrations, e to the power EF. EF, of course, in this case, it's flat in the semiconductor, minus EI. EI, EC, EV, they all move parallel to each other. And basically the EI is a measure of the band bending in the structures, right? The band bending is what I call phi over here. And the phi at the surface is what I call the surface band bending, phi S, all right? So all that I've done is I replace the P and the N by their exponential dependencies on EI, okay? In terms of the initial values, P naught and N naught, where P naught in this case would be NA, and the N naught would have been NI squared over NA as an example, okay? Or if you had donors also, N naught would be equal to ND, okay? The starting value. Now the NA and the ND, so I'm assuming the most general case will have both types of doping, give rise to this P naught, sorry, this is ND, okay? So those are the minus ones over here, okay? The NA and the ND terms over here. Okay, now once I have this differential equation, it's just integrating it from the interface between the oxide and the semiconductor, which I call 0, as a function of depth, x, and I integrate to some arbitrary location x, where the electric field is minus d phi dx. So all that I'm doing is I'm integrating from the interface where x equals 0 to some location x, where the electric field is minus d phi dx, okay? Of course, by the time I go over here, what is d phi dx? It's 0. So beyond that point, the electric field is 0. the space charge neutrality, and this term will give you 0. So all that I have to worry about is integrating from 0, the interface, up to the maximum depletion width, W max. Okay. So this second derivative, I can also write as d dx of del phi del x, okay, which of course is nothing but minus electric field over here, okay. So that's electric field d, there's a missing phi over here, that works to do d phi dx. So I'm integrating electric field d electric field, which of course will give you electric field square over 2, okay. That's what I have over here. And on the right hand side, I integrate with respect to x, sorry, integrate with phi, okay. That's why I ended up getting the phi over here. So initially I assume integral with respect to x, but then I change the variables and integrate with respect to phi. So I have the phi over here. That's what gives me the d e, and that of course is electric field. Okay, so on the left hand side, I get e squared. On the right hand side, since I'm integrating with respect to phi, I'll integrate from no band bending, phi of 0, the bulk, to some arbitrary point over here, phi, okay? And then take the limit, phi going to phi s, right at the surface, okay? As long as you get the general drift, that's fine, okay? I mean, I'm not going to, like I said, there's a complicated derivation that's done in detail in a graduate course. All that you need to do for this purpose is get a sense of how you obtain this curve over here, okay? And all that I'm saying is, you basically have to solve the Poisson equation, okay, with the right limits between the interface to the semiconductor to the point where there's no band bending, okay? All right, so if I take the limit of the surface, that's my surface electric field, and then I have the surface potential phi s. So the surface electric field is electric field at that point. That's what I call ES, and the band bending corresponding to that is my phi s. All right. And that gives you the electric field square. Therefore, the electric field would be the square root of this whole mess. Now, these integrals, although they look scary, they're not complicated at all, because luckily they're all exponentials, right? And we know that if you integrate an exponential, you get back an exponential times some prefactor, okay? But then I take the limits between 0 and phi. So when it's phi, I get this exponential. And then at 0, I get e to the power 0, which gives you this minus 1 over here, okay? On the other hand, when I integrate 1, I get phi, taking limits between 0, that'll be 0, and the other limit is phi, I end up getting these terms over here, okay? So, you should try to reproduce this integral and see, convince yourself that you get this, okay? Now, once I take the limit to the interface and I get the surface electric field, I can get the total integrated charge in one fell swoop, because that's equal to the dielectric constant times electric field, okay? And that's by using the Gaussian pillbox that you hopefully saw in 325, where all that I need to do is construct a Gaussian pillbox like so. I have the electric field ES over here. The electric field over here is 0, okay? Therefore, the difference of displacements would be epsilon semiconductor times surface electric field minus 0. And that will be the total enclosed charge, which I call this QS over here, okay? Therefore, the total enclosed charge will be nothing but the dielectric constant of the semiconductor times the electric field at the surface, okay? And that's what's shown over here. So that's making use of this Gaussian pillbox that hopefully you remember from 325, okay? Now, if you look at this expression, you'll see the origin of the various terms in the curve, okay? So initially when the surface potential was negative, minus times minus, that's the only important term. And because it's a square root, I end up getting this factor of 2 in the exponent. And that's this part of the curve over here, okay? When phi s equal to 0, let's see what do I get. When phi s equal to 0, that's flat band condition. I get e to the power 0, which is 1, cancels with this. Similarly, this cancels with this. I get square root of phi s. How about the second term? Well, the minority carrier concentration over majority carrier concentration initially will be negligible. So it's really the square root of this quantity, okay? On the other hand, when phi s is positive, this basically becomes unimportant. And when phi s is large enough, the most important term will be this one. In strong inversion, you'll get e to the power q phi s over 2 kt, okay? That's this term over here. While in between, it'll be the square root of phi s from this term over here, okay? Now, when you go to the math, you put a bunch of these constants in this parameter, LD, as shown over here, okay? And this quantity is known as your D by screening length, okay? Screening is a very important concept in semiconductor physics. It is a characteristic length scale in which charge imbalances are swept out, if you will. Okay, what does I mean by that? What I mean is, consider a positive charge in air that'll have a Coulombic potential 1 over R, right? But if I put this positive charge inside a semiconductor which is, say, doped N-type, where I have mobile electrons, what's going to happen? But these electrons will crowd around this charge, right? And if you move far enough away, I won't be able to tell that there was a positive charge in the middle. It looks like a neutral object, kind of like an atom, if you will, where the nucleus is screened out or shielded by all these core electrons and valence electrons and all that. And under these conditions, the potential will be a screened potential like this, okay? It'll go to 0 or a constant value earlier. So under these conditions, then, you'll get a potential V of R, which is not simply Q over R, but Q over R e to the power minus R divided by the screening length, LD, as shown over here. And as you can see, that depends inversely on the carrier concentration, N naught or P naught. Now, what did you expect if the carrier concentration went up? Did the screening be more or less effective? Now, clearly, it'll be more effective, right? Because if you have more mobile carriers that can crowd around, it'll screen out the effects earlier, right? Therefore, the screening length, which is the length scale needed to screen out these charge imbalances, would be reduced, okay? And it turns out, if you go through the math, the screening length appears over here. It's an important concept. Now, once I have all of this, I can now come up with an expression for the capacitance voltage behavior of this MOS cap. Let me sketch the structure. So that's my metal, my gate oxide, then I have the depletion region of a certain width, and then below that I have the undepleted semiconductor. So that's my effective dielectric thickness, which is made up of the actual dielectric and the voltage dependent semiconductor depletion region. And that's the undepleted part of the semiconductor. In this case, it's P silicon, right? That's what I've assumed. Let's see if we can understand the CD behavior of the structure. Well, if the gate voltage that I apply is negative, the VG is negative, I'll be pulling holes towards the surface. That's my accumulation region. And I get a capacitance, which basically is your so-called insulator capacitance, where this oxide or insulator will give you a CI equal to the dielectric constant of the insulator divided by the thickness of the dielectric, which I call D. Okay, so that is D. That's voltage independent. It's a fixed oxide. All right. As the gate voltage is made more and more positive, I start pushing the holes away and I start forming a depletion region. So now I get a composite dielectric, the fixed dielectric and this voltage dependent dielectric thickness. Okay. It's like two capacitors in series. So I have a capacitor CI or COX. I'll use those terms interchangeably in series with a semiconductor capacitance, which I call CD, because it's given by epsilon semiconductor divided by the depletion width W, which of course is a voltage dependent term. That makes this depletion capacitance a voltage dependent term. Okay, you have to be careful. Here, the dielectric constant is the dielectric constant of the oxide or the insulator. Here, the dielectric constant is that of the semiconductor. So in problems, you have to make sure that you don't mix up the two. And that's a very common error in homework problems or final exam. So there's a good chance I'll give you a MOS capacitor problem. So if you mess that up, I'll penalize you quite a bit. Okay. Now let's see how the CV looks like, okay? Well, for the voltage dependent part, as I've told you, the capacitance will be expressed as dq dv. While for the fixed oxide dependent capacitance, Ci, that's simply Q over V. That's not voltage dependent, okay? Now, if I take two capacitors in series, Ci and Cd, what is my overall capacitance? My overall capacitance, CMOS, which is what I'm showing over here, is equal to 1 over Ci plus 1 over Cd. And then if we invert the two, I'll get Ci Cd over Ci plus Cd, okay? And that's what's shown in this curve over here. All right. Okay, let's follow the curve. So as I go beyond flat band voltage, up to the flat band voltage, there's no depletion region forming. Once I go beyond that point, I start forming the depletion region, and that expands, right? And as the depletion region, the flat band voltage is over here. When I go beyond that point, the depletion region starts expanding. Epsilon semiconductor over W. W keeps going up, therefore CD keeps going down. So what would happen to the overall capacitance? That'll keep decreasing, right? That'll keep decreasing until you get the maximum band bending of 2 phi f, which corresponds to a maximum depletion width, which I call W max, okay? And that then gives rise to a minimum depletion capacitance, which I call C min, okay? So CD min. So CD min corresponds to W max, okay? Which corresponds to a band bending of 2 phi f, all right? And that gives you the minimum capacitance. Now, once I go beyond that point, as I said, the depletion region is not assumed to expand any further. Instead, what happens is I now start populating the interface with these inversion electrons, okay? And then you have to add the inversion charges over here, Q inversion dV, which is much larger, okay? Why? But you can look at this curve. The depletion region dq dv is relatively small. Then once I hit inversion, dq dv, which is this capacitance in the inversion region, is obviously much, much larger, okay? As a result, once I reach strong inversion beyond threshold voltage, the semiconductor capacitance keeps increasing. And once I have strong inversion, it's almost like a metal plate made up of these inversion charges. And you have the metal plate in the gate electrode separated by the fixed voltage independent oxide dielectric. So I'm back to C oxide or Ci. So that's a very useful curve showing the overall capacitance voltage behavior. Any questions? Now, from this curve, you can extract a lot of useful information about the structure, okay? So either from this accumulation capacitance or strong inversion capacitance, I can get the oxide thickness, right? Because Ci is given by the dielectric constant of the oxide divided by the thickness of the dielectric, D, which I'll sometimes also call Pox, because very often that's going to be an oxide, gate oxide, okay? So I'll use the terms D or Pox interchangeably, depending on the context, all right? From the minimum capacitance, it turns out you can also get the doping concentration. Now that's a little bit harder to get because what you have to do is, and we'll do that in the next class, we'll see that phi f depends logarithmically on doping, okay? So this quantity is 2 times kT over Q log of doping over Ni. How do I get that? Well, all that I need to do is to invert this expression over here. So P equals Na, the doping. EF minus EI is your phi f. Therefore, if I take the log of both sides after dividing by Ni, I'll get log of Na over Ni. KT is brought over to this side, and then Q phi f becomes KT log of Na over Ni. Okay, I know this is getting very messy over here, and we'll go over this again next time because it's so important. Okay. Now,
is the flat band capacitance something that you can read from that curve?
Yes, that's what I was going to end up with. right now I'm looking at this point, okay? So what I'm trying to say is from the minimum overall capacitance that's shown over here, you can extract the minimum semiconductor capacitance. But the minimum semiconductor capacitance corresponds to the maximum depletion with W max, which in turn corresponds to the maximum band bending 2 phi f, which depends logarithmically on the doping, okay? So from that, hopefully you can see you can invert these expressions and you can get an expression for the carrier concentration in terms of not the minimum overall capacitance, but the minimum semiconductor capacitance, okay? Now I'm not going to prove this. It's basically solving a transcendental equation to get this. So the steps are, from this minimum overall capacitance, you extract the minimum semiconductor capacitance, stick that back over here, that gives you the doping concentration in the semiconductor. Once I get the doping concentration, we talked about this quantity called the Debye screening length, which depends on the carrier concentration. So from this, once I extract the carrier concentration, I can get the Debye screening length, which turns out to be very important because, and I'm not going to prove this, it's important because under flat band conditions, the flat band capacitance is found to depend on the series combination of the oxide capacitance and this Debye capacitance, which is epsilon semiconductor over the Debye screening length, okay? Now I'm not going to prove this. It's a little bit, it's not that hard, but we don't have time for that, okay? So it turns out under flat band conditions, when you change the gate voltage a little bit, the bands bend around flat band a little bit, that gives rise to a so-called Debye capacitance over here in series with oxide capacitance, which is what I'm showing over here, okay? So knowing what the doping is, you can calculate the Debye length, you get the Debye capacitance, from which you can get the flat band capacitance, which you can then read off from this, and that then lets you read off what the flat band voltage is, okay? This is a very important curve, and I wanted to study that thoroughly, okay, because there's so much information that you can get. From the shape of the curve, you can also get the doping type, because it turns out, in this case, it's a p-type doping, and you can tell that because in the depletion region, the curve will go down slowly, but then once I hit inversion, it'll go up steeply. On the other hand, if it's n-type, it will be the mirror image. It will go down slowly and then go up steeply, okay? The final comment, it turns out this capacitance that I'm showing is true only if I do the measurement at low frequency. At high frequency, the capacitance wouldn't go up like this, it would stay flat. And I'll explain that as well as more details of this in the next curve, right? In the next lecture on Wednesday, okay? So in the next lecture, we'll keep talking about this, and I'll repeat a lot of what I discussed because it's so important, okay? All right, see you on Wednesday.
Did you explain how to read the flat band voltage from the curve?
Yes. So I said that from this minimum capacitance, you get the carrier concentration, right? From that, you get the Debye screening length. That enables you to define what's called the Debye capacitance, which is epsilon semiconductor by the screening length. That, in series with the oxide capacitance, gives you the flat band capacitance, okay?
Oh,
Once
but it's
again,
not something that you can read from the curve directly?
No, no. So you have to calculate it, and then it'll turn out to be somewhere over here. So you have to calculate that based on the doping concentration. Okay.
Okay. Got it.
And once you get the flat band capacitance, then from that you can read out what the flat band voltage is, which is very important. Okay. Which so far we have assumed to be 0 in an ideal structure, but in the next lecture we'll see it's not going to be 0 in practice. Okay. All right. Thank you.